Application of Gauss's law. Spherical symmetry, charged spherical shell. Objective: to find the electric field inside and outside a charge distributed uniformly on a spherical shell using Gauss's law. Consider a charge Q that is distributed uniformly over the surface of a shell of radius a. Let us calculate the field at a point P that lies outside at a distance r from its center. Let us draw a concentric Gaussian spherical surface of radius r that passes through P. From spherical symmetry, the electric field at every point on the Gaussian surface must have the same magnitude and it should point radially outward. Consider a small area ds on the Gaussian surface. Flux through this E bar dot ds bar is equal to E into ds. The total flux through the Gaussian surface is integral of E ds. Since E is constant everywhere on the surface, total flux is equal to E into surface area of the Gaussian surface, 4 pi r square. From Gauss' law, this flux must be equal to the charge contained inside the Gaussian surface by epsilon naught. Hence, electric field is equal to 1 by 4 pi epsilon naught q by r square. Hence, for points lying outside, the whole charge can be assumed to be concentrated at the center. Note, if the surface charge density on the shell is negative, electric field points radially inward. Let us calculate field inside the shell. Consider a point P inside the spherical shell. Draw a Gaussian sphere concentric with the shell that passes through point P. From symmetry, if even an electric field exists on the Gaussian surface, it must point radially outward and should have a constant magnitude E. Flux through the Gaussian surface, integral of E bar dot ds bar is equal to E into integral of ds, which is equal to E into 4 pi r square. This flux must be equal to the charge contained inside the surface divided by epsilon naught. But the charge inside the considered Gaussian surface is 0. Hence, field inside the shell is 0.